the city of Rockaway Beach. Welcome everyone in. We are very excited tonight. Well, everybody get a raffle ticket?
Yes.
Okay, so that raffle ticket is for a emergency preparedness prize to either add to your go bag or start your go bag. Okay, and we'll do that at the end. We have coffee back in the corner. One for each. Coffee back in the corner, help yourself to coffee. We are very excited tonight to have Dr. Johnathan Allen from DOGAMI here with us tonight. I've had a lot of questions in the last year about the geology of Rockaway Beach, what might happen should things go south. So I'm going to let him go ahead and introduce himself, but thank you all for being here.
Okay. Well, good evening, everyone. Thank you for the opportunity to come out here and speak to you about coastal geology. So my name is John Allen. I'm a coastal geomorphologist. I'm obviously not from hereabouts. I moved to the US 25 years ago and did a postdoc at Oregon State University. My background is in physical coastal processes. So what I'm going to do is give you a little bit of background on basic coastal geology, and then time permitting, I'll touch on tsunami because I know that's often an area of keen interest by a lot of people. So tonight's sort of topics is going to mostly focused on the role of physical coastal processes in changing our environment. And really this stems from work that I've been doing over the last 2 decades, but also prior to that, my colleague Paul Comer, who's one of the foremost experts on coastal processes, had spent his lifetime studying the Oregon coast. And so a lot of what we're presenting tonight really stems from his work, his students' work, and then some of the activities that I've been involved in. So you'll see on the image up here, sort of various examples of things that are going on today. And what I'd like to argue for tonight is that what you see today is almost certainly going to continue in the future and more than likely start to be expanded upon or become more catastrophic in some respects as other factors start to come into play through climate change. And so I'll touch on that. But we're already seeing along the Oregon coast here areas undergoing very extreme erosion. So the upper image on the top here is from the northern part of the Clatsop Plains, up by Clatsop Spit there. This is probably only about half a mile or so from the South Jetty, and this area has been eroding quite rapidly over the last 2 decades. And in all likelihood, we could see part of this four-dune system being breached in the next few years. The image on the bottom here is from Pacific City. There's a massive condominium complex here. They had actually, prior to building this structure, there had been riprap rocks placed in front of the dune here in the 1970s. So that was telling you something at the time about the problems at that location. And yet, development still went ahead, and as a result, now today they're starting to experience problems. And these types of responses are not unique by any means. I mean, we see this here in Rockaway Beach, up and down our coastline. The 3 images on the left are actually from a large storm, January 8th in 2008, impacting the community of Nisquam, just down the coast from here. And you can see a great example of waves running up, overtopping this riprap wall here. This backhoe trying to mitigate the problem during the storm, i.e. trying to fill the holes that were being eroded away. And you can see different examples of this leading eventually to a collapse of the riprap structure here. So these are the things I'm going to cover over the course of this evening. So provide a little bit of brief background about Oregon geology, the evolution of the coastline, talk a little bit about geohazards, the various types of coastal hazards that we see on this coastline, the various processes that drive erosion and change, And then really a lot of the work that I've been doing of late is how we document it and how we can use this information to make maps. Because ultimately what we're trying to do is take our knowledge of coastal change and turn that into hazard maps that can be used to safeguard against future development and reduce the risk from inundation, erosion, flooding, that type of thing. And then the last part, just time permitting, I can touch on very quickly on the tsunami hazard. So who we are. So my agency, it's a small agency, about 40 plus full-time staff. We're split into two divisions. What we call Program 1 is the geologic survey portion of the agency. And then Program 2 is what we call the Mine Land Reclamation Program. And Program 2 is really focused on regulating mining activities throughout the state of Oregon, including excavation for gravel and things like that that happens locally on the coast here, and using that aggregate for roading, etc. So that's that portion of it. I'm not going to talk about them again this evening. On the survey side of it, it's really divided into 6 programs. We have an earthquake hazard program, a landslide mapping program. We also have a team focused on channel migration, which is riverine flooding and avulsion, which is the moving of rivers out of the existing flood zones. And then the tsunami coastal hazard program, of which I lead up. Underpinning all that is our geologic mapping program. So that's where all the basic geologic mapping gets done, mapping different types of rocks along the coast or inland, using that information for mineral exploration and things like that. And then underpinning all this that really drives a lot of the mapping work that we do is the collection of what we call airborne LiDAR. This is where we contract with someone to fly across the landscape at a relatively low elevation. And rather than collecting imagery or pictures of the ground surface below us, they can use lasers to map the ground surface, from which we can actually then strip out the vegetation and look at the bare earth underneath. And this is a technology that's evolved quite rapidly in the last 2 decades, but it allows you an unprecedented insight into the geology and the geomorphic processes that are going on beneath that vegetation cover, which you would not normally see unless you were able to burn it all off and get rid of it. So that really drives a lot of the work that we do today. So with respect to the Coastal Field Office, we have 2 areas of focus, one directed at tsunami hazards. And within that, we do mapping and modeling. And so a lot of the maps, or all the maps that you see today, are the product of work that was done between 2010 and about 2013 to develop the standard sort of evacuation maps that you see today. And then since then, our focus has really been directed at doing evacuation modeling. So the idea is that for people in Rockaway Beach here, we can actually tell you for any given location in Rockaway Beach, and for that matter, anywhere on the coast, where you need to be going to reach high ground, how fast you need to be going, how much time you have, things like that. So we've spent a lot of time over the last several years perfecting that information, and we actually now serve that information via a web portal. On the coastal side of things, we've done a lot of work with basically developing hazard maps. We've worked for FEMA to update the coastal flood maps for the entire Oregon coast. The original flood maps were done in the 1970s using very poor quality data, much simpler models, and so we've utilized better data, better models to update those maps, and that's now being applied along the Oregon coast. We do basic fundamental science of observing what's happening on the coast. So if you see a little orange buggy that's got 8 wheels on it that's running up and down the beach here on Rockaway Beach, that's us. We're doing surveys measuring changes in the elevation of the beach and developing change over time maps to show our understanding of how things are evolving in this particular area of the coast. We also do a lot of work on landslide studies, and then we've been doing some new work focused on what we call soft engineering, which is focused on approaches that are different from the standard putting in huge rock walls or riprap structures, to protect properties. This is focused on using what we call dynamic revetments, which are essentially mimicking nature. So you can see an example down here. This is a Cape Lookout State Park. It's a park that's, the back of the beach there is covered in cobble. And so what we're trying to do is mimic nature, mimic that cobble by building similar types of structures in other locations. And we've had varying success with that, but it's a technology that's actually, or a technique that's now starting to be adopted around the United States, but also around the world in general. So a little bit of background about the Oregon coast. So the coast is approximately 365 miles in length. It can be broadly divided up into really four sort of thematic areas, four geomorphic classes. And if we start in the very far north, up on the Washington coast, we've got the Olympic Peninsula. It's dominated by rocky shorelines. As we come down from Point Grenville all the way down to Cascade Head, so encompassing all of Clatsop and Tillamook County, southwest Washington coastline, we have an area dominated by mainly duneback beaches like we see out here in Rockaway. As we get down to the central coast in the Newport, Lincoln City area where I'm from, it's mostly dominated by coastal bluffs. These are all marine terraces. And then you've got homes obviously being built up on top of those terraces to maximize view sheds. And then on the south coast, we have another section of duneback beaches like this. In fact, the Coos North Spit there is one of the largest dune sheets in North America. And then on the south coast, all the way down from Port Orford to Brookings at the Oregon-California border, we have another rocky coastline with plunging cliffs and other types of geomorphic features, cobble beaches and things like that interspersed in amongst the rocky headlands there. So out of these four geomorphic classes, we can identify these three areas that make up the bulk of our coastline. So roughly a third each is made up of sandy beaches backed by dunes, beaches backed by bluffs, and then to a lesser extent the rocky coastline. And in terms of geologic hazards, it turns out, well, okay, where those red circles are is where most of the people are located. And where people are located, especially when they're building close to the changing beach environment, that's when you start to experience hazards as coastal change catches up and starts to erode, as we see in this example here where a house is perched very precariously at the edge of that bluff there. So just a little bit of brief history about the Holocene or late Holocene history of the Oregon coast. So what we're talking about is the last several thousand years. So the Oregon coast that we see today is actually quite young. And we can document this through a variety of techniques. So this is a map of the southern Clatsop Plain. So this is where Gerhardt is located. Seaside is just south of the Mechanicsburg Estuary here. On the far right side of the image, we've got in grey there, you can barely see, we've got a series of marine terraces that were laid down somewhere on the order of about 20 million years ago. It's all marine mudstone and siltstone sediments. So it was basically where the continental shelf was at the time. And it's been uplifted over time. And then west of that is an area of accumulated sand, in this case here, the Clatsop Plains. And it turns out that you can date various features across these foredunes, which are all characterized in that sort of brown color there, these sort of lineaments that are running vertically from east to west to the present day coastline. So the present day coastline is in black. You can barely make out a dashed red line. That's where the shoreline was in the 1880s, prior to construction of the jetties. And so we have dates at the back edge here at around 5,000 years. 2,500 to 1,200 years ago, around mid-Clatsop Plains, out through here, out to the present-day coastline. So a lot of what you see today in terms of our beaches is actually very young. On the central coast, it's a little different. We have the same marine terraces like here, but we also have these eroded shore platforms. And it turns out that on these platforms, you can find evidence of buried tree trunks. And the most obvious ones are actually down by Nesquin, that you can see being exposed periodically in late winter typically, and sometimes they could be present even in summertime. But this is an example here from Nesquin. And it turns out that over the last several thousand years, These forests actually grew out across these short platforms. They were eventually inundated with sand, and then the ocean started eroding back into them and exposing and creating the beaches that we see down in the Nisquin area, exposing these tree trunks like this. And it turns out these tree trunks, which represent trees that are about 200 years, up to 200 years old when you count the tree rings. So they're pretty old. But the ages of these are on the order of around anywhere from 1,400 years down by Cape Lookout State Park to as old as 6,000 years down in the Beverly Beach and Newport area. So these forests were actually out in the intertidal zone at around that time before something happened. So I touched on one possibility mechanism for maybe killing that, and that was the influx of sediment. So this is an idea that was postulated by some professors at Portland State University. And then there's another complication in that, as we know, the Oregon coast is subject to the Cascadia subduction zone. We know that over the last 10,000 years, there have been at least 19 great earthquakes triggering tsunamis. And associated with each of those earthquakes, the coastline may drop by about 3 to 6 feet along the coast. And what you're seeing in this example up here, which is actually from some work that Brian Atwater did up in the Washington coast, you can see a record going back almost 4,000 years. And every one of these little blips corresponds to an earthquake event in which the coastline was dropped. And then in the intervening time, after that, building towards the next earthquake, the land is slowly rising up again. And in those time frames between earthquake cycles, it allows for peat and mud to accumulate in estuarine areas, and then forests may develop and things like that. So when we talk about the sort of 4,000-year evolution of the Oregon coast today, it's complicated because of these coast-seismic, what we call coast-seismic events that happen where the coast is dropped, tsunami inundates an area, and then the process rebuilds and starts again to the next cycle. So where does all our sand come from that we see on our beaches, given that the beach environment is actually relatively young? What we can do is we can actually look at the mineralogies in the sands, and we can start to sort of speculate about where sediment might be coming from. And we do this by developing what we call sediment budgets. And so this is an example looking southward from just up by Oceanside, south along Neatout Spit, Neatout Bay on the left here, Cape Lookout in the distance there. And what you can see is that, within this environment here, which is what we call a littoral cell, which is basically a headland-bounded stretch of coast in which sand is moving in flux. It's moving up and down in response to inputs, outputs, so losses, as a result of storms or storminess, stormy periods, and things like that. So within an environment like this, we can think of sediment coming in from terrigenous sources. So it could be landsliding off Cape Lookout. It could be erosion of the hills surrounding Neatout Bay and then being carried out by creeks. We can see erosion happening of cliffs up by Oceanside here. And we also have sediment inputs coming from the erosion of dunes feeding the beach system as well. We also have losses that are going on. These losses could be actually sediments being carried into the estuary, where over time it accumulates. We can also have losses being removed offshore into deeper water during the most extreme storms. It carries that finer sediment further offshore into deeper water, and it's much harder for it to actually return back onto the beaches. So when you look at something like this, you can balance up all these inputs and outputs, and what you find is that a coastline that is either eroding or accreting is a reflection of the state of this budget of sediments. It's like doing basic accounting that we do for our doing our own budget planning for our own lifestyles. So here's an example of how that might apply. So we can actually distinguish between coasts and beach that are either eroding predominantly or accreting predominantly, and then there's obviously those that may be somewhere in between. And so this is an example here. So if we look at Clatsop Spit, this is the original shoreline pre-jetty construction in the 1880s. And so all this sediment that's accumulated out of here is post-jetty construction. And so if we look at a time series, and this is actually taken from a transect near seaside. We've got time on the bottom. We've got the change in the position of the shoreline over time. Here are distances in feet on the right there. So what you can see is from around late 1990s up through to the present, this part of seaside has grown about 200, 250 feet in about 25 years. So that's a lot of sand that's accumulated in that location there. In contrast, we come down to Twin Rocks, just south of here, we have the reverse. This is I'm trying to think, what's the name of the Shorewood Park, RV Park? So if you looked at an image of this in the mid-1990s, this area was actually fronted by quite a broad sand beach. Well, this is a photo that was taken in 1999, and it turns out that this side has been actively eroding. In fact, some of the biggest erosion happened at this location, the 1997-98 El Nino winter, so about 27 years ago. And then since then, it's been very gradually eroding over time, and today it's cut back almost 200 feet from where it was 27 years ago. So again, these represent two extremes. And the point is that, you know, within these extremes, there's a lot of fluctuation going on as it changes in response to storms or other sort of climate events that may be going on. I don't know whether you've noticed it, but in the last 10 years, 15 years on the Oregon coast, in terms of storminess, it's actually been pretty quiet. We've had some of the quietest wave conditions in almost 4 decades of monitoring. And because it's been so quiet, a lot of our beaches have actually been tending to rebuild very gradually. Obviously, there are exceptions like Twin Rocks here. But in general, most of our beaches have actually been accumulating sand gradually over that time until we get the next cycle of big storms, which will happen at some point in the future. So again, I asked this question earlier, where does all our sand come from? Given that, you know, we have these littoral sows, these headland-bounded stretches of coast, and we have limited inputs into those environments. Well, it turns out that some researchers had looked at the mineralogy of the sediments that are on our beaches. And if you go out in late winter, great time to go, when the beach is actually being eroded down, you can see all these pretty colors in the sand, ranging from white, which tends to be quartz, through to black sediments, which are magnetites and things like that. But you can also see greens and pink minerals in that beach sand. Well, they reflect garnets and hypocene and things like that. Well, if you actually look at the concentrations of these sediments along the entire coastline, which is what Angela Clemens and Paul Komar did in the late 1980s, you can find that the concentration of garnet is very high on the south coast and progressively decreases all the way up to Tillamook Head, just north of us here. And then similarly, you can see hypocene in green here, this dash green, also decreasing all the way up to Tillamook Head. And then in contrast, you have this brown here, which is augite. And augite is actually locally sourced from erosion of the hills behind Rockaway Beach here, and then carried out onto the beach there. So this information is actually telling us something. It turns out that garnet is actually sourced from the rocks of the Klamath Mountains down in Northern California. So how did it get out here? How did it get on our beaches? If today's headlands are actually preventing sand moving around them, how might that garnet get into our beaches? Well, it turns out that 18,000 years ago, sea level was 400 feet lower than where it is today. So if you look at this map here, this dashed great line all the way along here corresponds to where sea level was at about 18,000 years ago, the peak of the last glaciation. So 400 foot. So that's where the coastline would have been roughly at the time. At around 8,000 years ago, so getting closer to the present, sea level was around 20 meters or about 60 feet lower than what it is today, which would place it somewhere around that pink line. So it turns out that, you know, our beaches that we see today are really the product of the last several thousand years. Again, going back to that map I showed of doing carbon-14 dating on the Clatsop Plains and other locations. So it's a very young environment, very dynamic though. So what are the hazards that impact our coastline? Well, they obviously vary depending on where you are on the coast. So this is Pacific City, And this is an area that's been influenced by excess sand because people built right out on the foredune there and were opposed to doing dune plantings to try to stabilize the foredunes. And they left it basically wide open. And so there were instances where sand would actually inundate these homes, in fact, even building to such an extent that it would pile up on rooftops, collapsing roofs and things like that in the Pacific City area. So that's a hazard. In other areas, we've seen evidence of extreme storms impacting our coast. So this is Cape Lookout State Park in 1999. And you can just barely see a riprap structure here. So in the 1970s, there used to be a actually, before the 1970s, there was a restroom there at the end of the 1997-98 El Nino. But they had to remove it in the following winter because of the erosion that was going on at this particular site here. But that restroom was built in the 70s. And in front of it, there was a massive foredune that was about 40 to 60 feet high, sitting out here. That's all gone. And so, again, that's a testament to the changes that are happening on our coastline. And it turns out that the southern part of Netarth Spit has been slowly eroding, well, not so slowly, relatively quickly eroding away, and the dunes have been peeling away to the north there. And eventually what we'll see is part of Netarth Spit being breached in an ensuing storm in the next few years. It could be years, it could be this winter, it could be several years, it could be 10 years, but it's soon. It's going to happen soon. And there's a history for that. It turns out that Netarth Spit had been breached pretty significantly in the 1930s. This is evidence of flooding during the same massive winter. This is Nesquin. Ground elevation here is about 5.5 meters, so about 16, 17 feet elevation. First floor elevation is around 22 feet. So you've got water, green water, basically growing through the ground floor of these condos here during a major storm. So again, this is a testament to nature and the care that's needed in terms of where you put property. In other places, this is the central Oregon coast, being Newport. This is where the bluffs, being bluff-back shorelines, they tend to be eroding at a much slower rate, on the order of 1 to 2 feet at the most per year. Actually, that's probably on the high side, less than 1 foot per year. That's probably a more realistic number. But we can see these were directional drill pipes that were inserted into the bluff here on a known landslide to help drain and dewater the landslide. And these were put in the early 2000, and this photo was taken in 2016, and so you can use that to give you a measure of erosion that's happening at this particular site there. But it's in this case here, it's probably 3 to 4 feet of exposed pipe now. So in this case, that's fairly quick, even in a bluff. In other areas, this is Glen Eden Beach, taken in 2006. We can actually see bluff erosion happening really quickly, as in over the space of the storm. So this is pre-storm. 24 hours later, this is what it looked like. Basically they had lost their entire backyard and they were scrambling to try to come up with a solution to mitigate and protect their home there. And in the end, they had to build a massive engineering structure, riprap wall, at the base of it to shore it up. And then, of course, landsliding is very common, and this is an issue that we see up and down the Oregon coast. This is the Three Capes landslide in 1999, and the same landslide obviously failed again in January of this year. And for a little while there, you were unable to travel along that road until they were able to address it. But this is an issue that obviously is very common on the Oregon coast. I mean, we've seen the effects of landslides affecting and cutting off 101 at Cape Foulweather, just north of Newport. They were shut down the highway there for several weeks. We had a massive landslide in the late 1990s down by Heceta Head that basically cut off Florence from the central Oregon coast for almost 3 months. So people were actually having to travel to Eugene and then back to Newport in order to get around that particular area. And so again, just thinking about Cascadia, when we would expect to experience massive shaking for sustained periods of time, that would almost certainly trigger many, many landslides, then the implications of being isolated, and we were just chatting about this earlier, being isolated is a big deal, and that communities need to be thinking about those types of worst case situations as they develop their emergency plans. So what's driving all this? So there's a whole suite of processes here that really drive the coastal responses that we see. These range from, not surprisingly, big storms, heightened sea levels that could be as a result of experiencing El Nino events, storm surges. Storm surges on this coastline are generally fairly mild, as in within a couple of feet. If you go onto the east coast, especially in hurricane activities, you'll see storm surges on the order of a few tens of feet. So much different environment to what we experience out here. And a lot of that's to do with the broad shelf and shallow fetch that accentuates the storm surges on the east coast. We don't have that same characteristic out here, thank goodness. We also experience very significant movements of sand within our littoral cells, as well as movement of tidal inlets, river mouths. And then we can actually experience hotspot erosion as a result of rip abatement. So I'm sure many of you have sort of walked out, particularly in springtime, May, on our beaches around here, and you can see these re-entrants forming where there are localized scouring of the beach down. You can see jets of water going offshore, and we can see the effects of that erosion at the back end of the beach close to those. So those are rips that develop and can actually further accentuate and accelerate erosion at unique locations. And we see the movements of those rip abatements up and down Rockaway Beach here, even up on both Bay Ocean Spit and Nestucca Spit. They're obviously never staying in one location. They're driven by feedback from offshore bars and features like that sets up a feedback with the currents and water levels and so on, and help perpetuate those types of processes. But they tend to form, particularly in springtime, as we transition from the eroded winter state, when the beach is at its lowest elevation, back to its accreted state in post-summer. And then, of course, sea level rise is another big deal. So what's our wave climate like? Well, I mean, the Pacific Northwest is exposed to one of the most extreme wave climates in the world. Our winter waves characteristically can reach as much as 45 feet. We haven't experienced, actually, I tell a lie, 2 weeks ago when we had that big storm, there was all the talk and hype about a bomb cyclone, which was certainly justified, but it definitely caused a little bit of panicking by people. Those types of events can actually produce large wave events, and off Tillamook here, the waves actually reached about 35 feet, and we haven't seen that for about 10 years or so. So that was, a big deal. In general, as you know, summer months, water levels and waves tend to be lower. So our wave heights are around 1 to 2 meters, so about 5 or 6 feet on average. So this blue line here is the average. The dashed line is 1 sigma, 1 standard deviation inside of that. So basically about 68% of the waves that get measured are within this boundary here. And then these events here are really associated with very low probability or very few events. Less than 1% of our waves are associated with these big events. But nonetheless, they're very important, as we see in the images on the right there. We also see very significant differences in our sediment transport. So the image on the left is the normal pattern. So here's we got a headland-bounded littoral cell. In the winter months, our waves come out of the west to southwest and tends to erode sand from the south here and drives it north. In the summer months, we have a reversal. The winds come out of the west to northwest, and that flow drives things back to the south. And so over many years, these conditions sort of balance out. Well, in El Nino years, which happens roughly every 10 to 15 years, we can get more enhanced processes. And in particular, we can experience much larger waves coming out of the south to southwest. It causes more significant erosion, more sand gets driven to the north. We see our bay now starting to move northward and so on. And the reality is that in the years following these types of El Nino events, the beaches don't recover as quickly. It takes much longer for them to recover because the events are actually moving so much more sand in general. The image on the far right there, oops, going back, is just a plot of wave direction, just reinforcing the points here. So this is the summer months, waves coming out of the west to northwest. In the winter months, waves coming out of the west to the southwest. And you'll see that the biggest waves, which are on the order of 30 feet plus, are predominantly coming out of the south-southwest direction. And these are the ones that really are most concerning. So I touched on this conceptual idea of sand being eroded from one end of a pocket beach. So if you think of the Rockaway cell. So Rockaway is made up of what we call three subcells. In the very far south, we've got Cape Meares, and we've got Bay Ocean Spit. Then we come up to Rockaway Beach, then you've got Nehalem Spit in the north, and Neakani Mountain forms the northern barrier. So that's your littoral cell. So the whole idea is that within that little littoral cell, we wouldn't be seeing any sand coming in from Cannon Beach to the north or Netarts to the south. So what you see is what you've got, basically, in this littoral cell. So in an El Nino, what happens is because those big waves come out of the very far south quadrant, we see more erosion happening down by Bay Ocean Spit, at the south end of Bay Ocean Spit there. We also see more erosion happening north of Tillamook north of Tillamook Bay, north of the north jetty of Tillamook Bay. And so from Tillamook Bay up to about Twin Rocks, even as far north as here, we see enhanced erosion taking place. And then those sands get transported northward. So you go up to Manhattan Beach, you'll see a beach that's very wide, relatively stable, broad expanse of dune in front of all those houses there. And that's the product of sand being transported up there and then being trapped by grasses and things like that. And then you see the same process happening north of Nehalem Bay going all the way up to Manzanita. So this image here is really capturing these types of changes. This is from the 1997 through 2002. And we see erosion happening in the central part of Bay Ocean Spit and massive accretion happening on the south side of Tillamook Bay there. On the north side, massive erosion taking place, and then that decreasing northward. And then same sort of process happening along the Nehalem Spit there in the far north. And it turns out that this particular winter season, we saw a net loss of somewhere on the order of about 1.5 million cubic meters of sand, which is almost 2 million cubic yards of sand was removed from the beaches here. And most of that sand was being actually removed offshore to form the offshore bars and things like that. Well, it turns out that, that little snapshot that I showed you, which was just a few years window, that's the few years window. And this is the major El Nino from 97, 98. But in the last 3 or 4 decades, there's actually been other major El Ninos, one beginning in 1982, 83 here, another one in 2010, 2011, there's another one in 2015, 2016, that's off the map here. But it turns out that these El Nino events tends to result in a net northward progression or northward drift of that sand. And so we're not actually, that conceptual idea of sand returning back to the south ends of these littoral cells is for now not in fact actually correct. That in reality it's much more complicated because of these climate cycles that are going on. And so it turns out, and this is a case study that was done here in the Rockaway cell, the net movement of sand has been towards the north, towards Neakani Mountain ultimately. So it's complicated. So if we look at the water levels, that's another major factor of consideration. So in a normal year, we have cold water upwelling along our coastline in spring and summer months, and that depresses basically the ocean water level. Colder water just depresses the water surface. And as you go into winter months like now, that ocean upwelling breaks down, and in fact our water temperature warms up. And the difference is about 3 or 4 degrees centigrade. And so it turns out that difference is enough to actually raise our water levels by about half a foot to almost a foot between summer and winter. In an El Nino year, as we experienced in 2015, 2016, and before that, our water levels can be raised almost 2 feet. And that's because of enhanced ocean upwelling, enhanced ocean water temperatures that accumulate along the Oregon coast, and it elevates water levels because of that. That 1 to 2 feet is actually very critical because it's coinciding with when our big winter storms hits our coastline. So it's happening right around December, January, February timeframe when these water levels are at their peak. And so you can see here in the 97, 98 El Nino, water levels almost were 2 feet above normal. And that's very significant. That's basically raising the height at which waves are able to reach at the back of the beach, and is a major factor contributing to the erosion problems that we see up and down the coast. If we add in sea level rise on top of that, then things start to get even more complicated. So it turns out that sea level along our coastline is non-stationary, meaning that the rate of sea level rise is varying along our coastline. And this is because purely to do with our location close to the subduction zone and the regional tectonics that are going on underneath our feet here. So for example, the image on the left there is actually the tectonic uplift along the entire length of the Oregon coast from essentially the mouth of the Columbia River up here all the way down to the California border in the far south. And what you see is that up by Astoria, north of Tillamook Head, tectonic uplift is about 3 to 4 millimeters per year. It doesn't seem like much, but it's happening. On the central coast, like where we are now, including Tillamook County, the rate of uplift is about 1 millimeter per year, so much slower. A lot of variability, of course. And then it reverses again south of about Coos Bay, where the uplift rates increases again. Well, we can use this data and we can extrapolate sea level trends from satellite data, and we can develop a relative sea level curve for the whole Oregon coast like this. And so what you find is that north of Tillamook Head, the coastline is basically very gradually being uplifted, and it's rising faster than sea level rise. On the central coast, that includes Tillamook County all the way down to Lincoln County, the reverse is happening, where sea level is actually outpacing the rate of tectonic uplift. And the rate of uplift is around 1 to 2, the rate of sea level rise is around 1 to 2 millimeters per year, which again doesn't seem like much, but that's the present day environment. And then south of Coos Bay, we see it actually being an emerging coastline. So we see these two contrasting images for the Tillamook County area. One is, if you look at Nehalem Bay today, this is in a king tide in the middle of winter, around December timeframe, and we see the evidence of flooding that's going on there today. And this is being enhanced by other factors, not just sea level rise, but climate change through changes in precipitation as well. On the south coast, it's the opposite. It's an emerging coastline for now, anyway. And at some point in the future, we can expect these processes to reverse so that this area starts to become inundated as sea level rise accelerates. So what are the projections for the future? So here we are today. We're experiencing these very gradual rates right now. But the forecast is by around 2050 that we can expect to see around half a foot to almost 3/4 of a foot rise in sea level. As we go out to 2100, we're now looking at around 2 to 3 feet potential rise in sea level. So that's just the basin response, the global response to sea level change over that time frame. I touched on earlier about the role of El Niños. El Niños happens every 10 to 15 years, and it raises our water levels by about 2 feet. So now you've got 2 feet happening on top of sea level rise. And again, what we're doing is we're basically elevating the height at which waves are able to reach at the back of the beach, contributing to more enhanced erosion and the problems that we see today being analogues for the future. The variation in colours here is simply the uncertainty band. So there's still a lot of uncertainty about these projections going out in the future. But over time, what we're seeing is that they are progressively producing larger numbers from where they were 10 years ago, when the initial predictions were starting to come out for the Pacific Northwest in terms of sea level change. So it's gone up slightly. But there's still a lot of uncertainty, and that's a reflection on how society is going to handle climate change going forward into the future, in terms of trying to switch to renewable fuels and those types of things that could change and potentially slow down these patterns over time. And a lot of that is reflected in the various types of climate models and how they treat future projections of increased carbon dioxide in the atmosphere and then the associated impacts of that. So, best case situation, if society were to change things now and switch immediately to renewable fuels, move towards electric vehicles, that type of thing, then we might be experiencing something down in this range in terms of future responses. If we don't do anything, then we could be up into this range for the future. And this is, these are the situations that we're grappling with as a society. So what can we expect from the future? So a lot of what we see today is really an analog for the future. Obviously increased erosion. We're already seeing major problems like this up and down the coast of Tsunami Beach, putting in a riprap structure to protect these houses up here because of failure of the bluffs. This is a riprap structure in Nesquin that's failed in a big storm, and these guys are now trying to put in emergency protection. This is just down the road here where erosion has caught up to this particular house. They eventually got a permit to put in riprap. This is the Sika Beach, one of the fastest eroding sites on the Oregon coast. And then of course, engineering, trying to protect jetties in a big storm down by Coos Bay, and then the flooding problems that we've seen in places like Nehalem today. So what can we do about it? I mean, how are we actually documenting these changes in terms of the impacts on the coast? So we understand the processes, but what's actually happening on the ground? So we use a variety of techniques to measure change, and these range from using GPS to georeference to receivers on jet skis that allow us to map out through the surf zone at very precise, with very great deal of precision. We can put GPS on top of backpacks, and we can walk out across the beach there. We can mount it on a vehicle and measure shorelines and other features. We can use laser scanners to map the back of the beach. We can use aerial photos to go back in time, and we can use much higher resolution data like LiDAR to map entire swaths of the coastline. So we use all this data, but what I'm going to show you is some results from using backpack mounted approaches. So we, and like I said earlier, you probably see us from time to time driving up and down the beach here in a bright orange 8-wheeler. That's us doing our surveys. We're legitimate, we have permits, and we're collecting data. And we've been doing this now for almost 2 decades. And so this is an example from just south of here, this is offshore from by Camp Magruder. This is our Transect Rockaway 2 site. And there, what you can see here is change over time. So in the bottom graph, we just start here. This line up here is where it was in 1997. And the black line is where it is here today. And if you look at the change at the back of the beach, right up here, this is the tree line at Camp Magruder. And this area here is cut back almost 150, close to 180 feet in 20-something years. And as you go down the beach, getting closer to the intertidal zone down here, this is where you see a lot more variation. And so you can see that between summer and winter, this beach down here is actually eroding as much as 30 to 60 feet from summer to winter. That's the standard sort of seasonal response that we see up and down the coast. So when we try to make projections about what's happening going forward into the future, this is what we're mostly interested in. So down here, this is being driven by tides and seasonal variations and waves. What's happening up here at the back of the beach is being driven by storms, sea level rise, long-term climate effects, things like that. And this is really where we need to focus our attention when developing maps for the future. So how do we do this? We can actually map a shoreline right along this sort of wet grey line here, down by the waterline here. We can also look at changes that may be happening at the back of the beach there. And as I said, one measures storm responses, one measures the seasonal type responses. And we've done this for all of Tillamook County. So the image on the left here is that we can take all our shorelines that we measure and we can develop maps. And it's very hard to see at this sort of scale here, but this is all the way from Nesquin, Cascade Head up to Neahkane Mountain. Neetat's in the middle here. Here's Rockaway Beach, Tillamook Bay, Nehalem Bay up here. The red colours indicate erosion. The dark blue colours, like here, indicate accretion. So visually what you can see is and the sort of the grey shadings is either low rates of erosion or low rates of accretion that's happening on. So it's within the noise. And so what you can see is that places like Nesquin are eroding very gradually, but as you come up to Neetat Spit, the rate of erosion increases quite dramatically. So here's a close-up of Neetat Spit here, with rates of erosion exceeding 6 to 9 feet per year in some locations. So pretty high rates. And then of course you on the north side, we see up by Oceanside much slower rates there. We can also do this using our backpack surveys, and we can find rates of change. So this is Nitats here, Bay Ocean Spit. So Bay Ocean Spit is actually accreting at up to 10 feet per year right now. South end of Rockaway here is eroding at around 4 to 5 feet per year now. But we see these reorientations where basically the beaches are actually eroding at the south ends and building in the north. So that our beaches are actually reorientating themselves to the predominant wave environment. We're going to skip this one. It's basically saying the same thing, but now scaled up for the entire county coastline. So we can use these data to start to make projections about what's happening in the future. And so we did this back in 2001 for Tillamook County. We use a simple 4G erosion model that basically takes the offshore wave heights. We define certain scenarios. We calculate the wave run-up based on those offshore wave heights using information about the slope of the beach. And then we can project that out into the future, assuming a 50-year or 100-year time horizon or some longer-term horizon. And we produce these, what we call an active erosion zone, a high hazard zone, moderate, out to low. So we've done this for Tillamook County. So this is an example from south end of Twin Rocks here. So these, I'll just point out, in red is that high hazard zone, in orange is the moderate hazard zone, and in yellow is the low hazard zone. So again, red is what we anticipated might happen in 50 years. Orange is what we might expect in 100 years. And yellow is an extreme incorporating co-seismic response through a Cascadia event. This was mapped in 2001. And so the beach was actually right at the juncture, at the western limit of that red line. That's where the beach was. And so what you can see right away is that the beach is actually cut back at this location. This is Camp Magruder down here. Virtually that entire distance of our high hazard zone. So that's telling us now that we're actually underestimating what we produced 20 years ago. And we need to be thinking about updating these maps to incorporate better data. And we're actually starting to encroach into our moderate hazard zone in some locations. At the opposite end of the extreme, this is up by Manzanita. So again, our original shoreline was out here in 1998. And this is the present day dune line that's in front of it now. And that's all that accretion that I touched on before. All that sand that's been moving northward up along the coastline is now building up by Manzanita. And they're actually benefiting from the losses that you're experiencing down here in Rockaway Beach. And so up there, our hazard zones are actually now, one would expect to actually move them probably further seaward if one were wanting to, update these and modify these. And we can do this for different types of scenarios, incorporating sea level rise and make new predictions. This is something we did in 2012. So now utilizing more up-to-date imagery of the coastline, and you can see our erosion zones now much, much wider when you start to factor in sea level rise and extreme storms into the scheme of things. So these are available now to Tillamook County and to the cities for planning purposes as they consider future developments. So where can I find more information about this? Well, there's lots of different sites. You can go to the Oregon Department of Geology. There's a publication search there. You can find information about reports and maps that have been produced over many years. You can go to the nanus.org and use their beach mapping tool. And you can click on any one of these points here along the Oregon coast, and you can pull up maps showing what's happening at each of those locations there. So every dot corresponds to a site where we're actually actively surveying and have good information about change at those locations. And you can also go to our HazView site. You can look at the maps themselves in a portal and use that information to guide decisions and things like that. So I'm going to switch quickly to tsunami hazards. And so as you're all well aware, the Oregon coast is subject to two different types of tsunami hazards. One is what we call distant tsunami hazards. These are generated by far-field earthquakes. So the best analogy is what happened in 2011 in Japan, in Tohoku, with the 9.1 earthquake that happened there. That triggered a tsunami that caused catastrophic damage in Japan, but also triggered a tsunami that traveled across the Pacific Ocean and impacted our coastline. And luckily, it coincided at the time with low tide, and so the impacts, at least in this part of the coast, on the central to north coast, was actually pretty mild in the scheme of things. It was mainly a beach event. It was a situation where you get off the beach and get inland of our orange tsunami hazard zone. On the south coast, it was actually much worse. It actually caused a lot of damage in the ports of Brooking Harbour and Port Orford, almost $20 million worth of damage down there. The wave heights were about close to around 10 to 12 feet, even at low tide. Whereas up on the central coast, it was only a couple of feet in height. So imagine what might have happened on the south coast if that same event had happened and coincided with a high tide. The damage would have been pretty catastrophic for places like Brookings and Port Orford. So in the case of distant tsunami events, timing matters a lot. And we saw an example of this in the 1964 Good Friday earthquake that happened up in Alaska, triggered again a massive tsunami, impacted our coastline, actually in that case close to high tide, caused quite a bit of damage up in Cannon Beach area, and then also up in Seaside. So those are distant events, and they're mainly affecting our coastal beaches and our low-lying sort of maritime ports and harbours. And so in our maps that we produce, when you look at them, we've got an orange zone for our distant events, we've got a yellow zone for Cascadia, and then we've got a green zone for safe. So if you're thinking about evacuating for a distant event, the main thing to appreciate is you'll have time to respond to that. And you really, your goal is to get off the beaches and get out of that orange zone. So that's the main thing to take away for distant events. And the other point, of course, is that you're going to hear about it. And you're going to hear about it through social media. You're going to hear about it through CNN. All the TV networks will be on it so fast. And of course, then the emergency responders will be able to broadcast sirens in those communities that have sirens, or doing reverse calling where you can sign up for enter your phone number, and then they can send out a mass message to all of you to say, hey, heads up, something's happened. So that's a distant event. But of course, what we're really most worried about is what happens in a major Cascadia event. And like I said before, in Oregon, we have, in the Pacific Northwest in general, we have one of the most comprehensive data sets of geologic evidence of past great earthquakes on the subduction zone going back almost 10,000 years. And a lot of that information stems from work that's been done in various coastal lakes and estuaries along the entire length of the coastline, as well as a lot of coring work that's been done by Chris Goldfinger and his students at Oregon State University, developing these chronologies of events that can be then calibrated with other events on land to look at their relationships. And the main point to take away from this is that when you look at the geologic evidence, it's not about looking at one particular site and what's happening at that one location. It's looking at the chronology of that same event across the entire Pacific Northwest coastline and doing all the wiggle matching to ensure that we're consistent with these events, and we have good dates on those and things like that. And this is an area where there's actually a lot of ongoing research that's going on today to really try to refine the dates and then also constrain the estimates of how much the land might lower in these great earthquakes. And as I said earlier, general estimates right now are about 3 to 6 feet depending on where you are on the coast. So we've done, we put together a team in early 2009 to develop updated maps of the Oregon coast. We used the geologic evidence from these offshore cores and on-land cores. We use various models of how the earthquake might rupture. We use information from estuaries about how much the coastline might drop, and so this is evidence here of around 1 to 2 meters, so about 3 to 6 feet, based on known data, which is in that dark shaded band here, from the Washington coast all the way down to California, and then we can scale it up from that to reflect different types of scenarios. So we took the full 19 events, and we basically binned them into 5 what we call t-shirt sizes. And they range from what we call small, medium, large, extra large to extra, extra large. And that was how we parameterized these earthquakes, these 19 great earthquakes. And we then assigned estimates of how much slip would occur And slip is basically in the downgoing plate. What's happening right now in the downgoing plate, the two plates are currently locked, and strain is building up over time. And that's why we have this tectonic uplift that's going on. When that strain gives way, which happens roughly every 500 years on average, then that energy is directed up dip of the subduction zone. And that's what actually propagates the tsunami, because that uplift comes up to and pushes up the water column. And that's what triggers the tsunami ultimately. And so we can use these different models to actually characterize those types of responses. And so we bin these 19 events into 5 classes. We assign the amount of slip that was based on how much the two plates are coming together. And then we run the models and produce inundation maps, which is the products up here. And then from that, we can actually develop the evacuation map products. So how long will the shaking last? Well, based on, it's really a function of the length of the subduction zone. And this subduction zone is about 1,000 kilometers in total length from California all the way up to the top end of Vancouver Island. And if the whole subduction zone were to unzip, then we could expect this to experience about 3 to 5 minutes of earthquake shaking. And just for comparison, this is a time series of the rupture process for the 2004 Andaman, Sumatra Andaman magnitude 9 earthquake. This is 600 seconds, which is about 10 minutes. This is the Boxing Day event that happened in 2004, killed over 200,000 people. In contrast, the 1964 Alaskan event was about 160 seconds here. And then, of course, the Tohoku event was slightly less, at about 150 seconds. So we're talking minutes here. For Cascadia, we think it's somewhere in this light blue shaded area, so somewhere on the order of 3 to 5 minutes. How strong will the shaking be? Well, in terms of predicted intensity shaking, we can experience anywhere from strong to violent shaking. So violent shaking would result in catastrophic damage to many buildings. The area of the coast that is most likely to experience this is down on the very southern Oregon coast in Curry County, primarily because it's much closer to the subduction zone, and the earthquake shaking down there is going to be more severe. Up on the central to north coast, we're more likely to be in the very strong to severe category, which is still bad in terms of potential for damage to buildings and things like that. And essentially, in an event were it to happen today, happen now, the approach would be to drop cover and hold on, ride out the earthquake shaking, and then of course evacuate quickly and rapidly up to high ground as fast as you can. What can we expect? We only have to look at Japan in 2011 to get a sense of the scale of damage that could happen on our coastline. And so here's examples where the waves was inundating the Sendai Plain. This particular image here is almost a direct analogy for seaside. Multiple bridges, the coast is out here. These bridges that are up in seaside there are likely to fail in the earthquake shaking because they're designed pre-1990 pre-1990 code. And so they're unlikely to survive the earthquake shaking intensities. And then we could see inundation that could be on the order of tens of feet, depending on where you are on the coastline. So this is the emergency operations building out on the Sendai Plain. This is a very famous photo. People who were inside this building, virtually everyone died except for about 10 people that climbed a flagpole up here to get above the inundation height. And so this was obviously a catastrophic loss in terms of their emergency preparation planning activities. What are the impacts? It's bad. I mean, there's no way to couch it. It's bad. We have about 200,000 residents on the coast. We experience anywhere from 200,000 to 400,000 visitors in summertime. Of these, around 25,000 to almost 60,000 residents are in the inundation zone. And then if you factor in all the hotel, motels, VRBOs and things like that along the coastline, we could experience anywhere from up to 100,000 people on the coast vacationing at the time this event could go off. So the potential is there for large loss of life. So we've done estimates in terms of fatalities for different parts of the coastline. We've done this for both our medium scenario, which is the most likely event to impact our coastline. Of all the 19 events, this is the most common event in that long record. And we could experience anywhere from 4,000 residents to as many as 15,000 people when you factor in visitors as well. And then it climbs substantially if we think about XXL, which is our most conservative inundation maps. A lot of people potentially displaced, and in terms of losses, just the coast alone is somewhere on the order of 35 billion to almost 45 billion in terms of losses. And in comparison, if we look at Japan in 2011, which is on the right here, Japan is one of the most prepared countries in the world in terms of earthquake preparation, seismic codes, things like that. They also drill extensively. Every year they run drills in every community, and their community is very, very well prepared for tsunami. Yet they still lost 18,000 people. And it turns out a lot of the losses, a lot of the lives lost was because of unfortunately, through a combination of poor engineering. There was a reliance on seawalls, there was a reliance on certain structures, vertical evacuation structures that weren't built high enough. There was miscommunication. There was people who left the inundation zone, were trying to find their loved ones, and went back into the inundation zones and died because they went back into the inundation zone. So there's certainly a lot of lessons learned that we in the scientific world have taken from Japan, and our emergency managers are really using this as the direct analog for what could happen in Cascadia. And so these are the things that we need to prepare for. Some numbers for Tillamook County, and I apologize, it's probably not very clear here. Luckily in Tillamook County, in terms of potential fatalities, it's much lower relative to, say, Clatsop County, and particularly Seaside. We could experience around 500 residents to maybe 1,200 residents, but then it climbs once we start to factor in numbers of visitors. So, at best, a few thousand people. At worst, it could be several thousand people, in the worst case situations. Again, one of the things that communities like Rockaway will have to deal with is the numbers of people displaced. And it's not just those who lose their homes in the inundation zone, it's those that lose their homes because of the earthquake shaking. Many of our homes were built in the 1960s, 1970s, pre-code, and are just not built to the standards that would essentially allow one to ride out an earthquake today. And so the expectation is many homes, even though they're stick-built and tend to ride out the earthquake shaking quite well, the fact of the matter is you probably wouldn't be able to go back into them after the event anyway, because they're still going to be compromised. And that's one of the issues that our communities on the coast are going to have to deal with, is the potentially very large number of displaced people, which could run in the sort of tens of thousands, especially when we start to factor in visitors. You think of Rockaway Beach here in the middle of summer, and all these VRBs are full, hotels. Who's going to take care of them? Unfortunately, it's you all. Because Highway 101 is going to be cut off, and we were chatting about this with Jeff earlier today. Highway 101 is going to be cut off, and so people are going to be having to survive with what you've got in this area. So you need to be thinking about that and planning for that. And there's lots of other information there about losses and damage and things like that. And then we can compare this for up and down the coast. So here's Tillamook County in terms of fatalities, separating visitors in dashed here with the solid colours being residents. So, Tillamook County, like I said before, will tend to ride out the human losses relatively well when compared with, say, somewhere like Clatsop. And you think of Seaside, one of the most exposed cities on the Oregon, the most exposed city on the Oregon coast, where fatalities are likely to be, pretty severe. And then, of course, as you go up and down the coast, it varies quite substantially. So some success stories, a lot of the information that we've developed in terms of evacuation maps and things like that are easily accessible. So we started putting all our products, all our maps online in 2009 when we first started rolling out maps. This is the early iteration of the maps there, and then we actually built something that's much, much more functional today. This is on Nanos, it's hosted by them, but all the data that we generate is fed into this. The cool thing about this is a map of Seaside. When you go to the portal and you can scan the QR code there, You can, on the web-based version, so on your computer, you can actually enter a physical address and it'll actually tell you whether you're in the inundation zone or not. You can also click on the map, anywhere in the map there, and it'll produce the same information. It'll tell you whether you're in the zone or not. But more importantly, and this is the great thing about it, is that it actually now produces an evacuation route. So I can go to this map, I can click on the Esplanade and downtown Seaside there and say, I want to go here. Click on the map, it'll produce a route, it'll tell me exactly where I need to go. It'll tell you on the right there how fast you need to be going, whether it's a walk, jog, or run. So, when we talk about evacuation, we practice our evacuation drills. Most people talk about, walking out of the inundation zone. Reality is, you need to be going as fast as you can humanly possibly go. If you can run, run. Because every step you take in the direction of high ground increases your chances of surviving this event. And this event is survivable. I mean, when I first started doing tsunami outreach and working on evacuation modeling and things like that, what I noticed was people were very pessimistic about surviving this event. What I can tell you is that it is survivable, but you need to know some basics. You need to know where you are at all times. If you're in the inundation zone, you need to be able to know your evacuation route. You need to know how quickly you need to get there, and you need to practice it. And that's all you need to do in terms of preparation. Of course, then you should have your go bag and be prepared to be isolated for at least 24 hours, maybe even up to 72 hours. And then there's all the other stuff that happens beyond that, days to weeks in terms of recovery. And so you need to be planning for all of that. Oregon Emergency Management now tells people to be prepared to not experience any help from the federal government for up to 2 weeks. And I think that's probably conservative, to be real about it. So the information is out there. You can dial us up for any location on the Oregon coast. We've even produced this working in collaboration with Washington DNR. You can even bring up maps now for the southwest Washington coast as well, and they have a bigger problem up there because high ground for them is much, much further away than it is on our coast. We're very fortunate that because of our unique geology and geomorphology, high ground is accessible for most places on the Oregon coast, and we're lucky in that respect. So these data are being used to develop these maps. You'll see signs. This is up by Canna Beach here. We've got blue lines. We work with schools to establish blue lines. So you can see in some locations these blue lines on the pavements there. That tells you where you're leaving the inundation zone, and safety, of course, is above it. They're using these maps to develop mass care planning. So Manzanita is doing this. City of Rockaways is going down this path as well. In some areas, they build vertical evacuation structures, such as down at the Marine Science Centre in Newport. And then, of course, we can actually use this information to, guide signage. And a lot of the funding that we can provide communities is through purchasing more brochures and putting in signage on the ground and helping to, improve your chances of finding your route. Because that's one of the challenges, is when you're standing out here in the middle of winter, it's pouring with rain, and you're out by the beach, and everything else is dark around you. Where's high ground? And you need to be able to, get to 101 as quickly as you can, and you need to be able to see those signs along the road pointing you in the direction of where high ground is. So, I know that there's a lot of debate goes on in coastal communities about sign saturation. Well, I would argue sign saturation, especially for the tsunami hazard side of things, is critically important. There needs to be more of it because you need to be guided. Again, middle of winter, pouring rain, it's going to be tough out there, and so you need to plan for that. And I'll stop there. I've talked too long. I'm happy to answer any questions. Ma'am?
I'm wondering, what could we expect to happen to our local hillsides during a major earthquake?
Yeah, that's a great question. And so the best analogy I can give you is look at what happened in New Zealand in 2017, I think it was, when they had the big Kaikoura earthquake. And that caused about 3,000 to 4,000 landslides in the northeastern portion of the South Island. And all those landslides cut off the major highway that travels down the east coast of the South Island, New Zealand. And it was shut down for months and months and months. So the analogy is I would expect something very similar to happen here. Specifically at this location, you would actually need to, do some engineering type studies to look at the landslide risk and landslide potential. We've developed maps. My colleague Bill Burns in my agency has done a lot of landslide mapping. In fact, they actually updated all the landslide mapping for Tillamook County a few years ago. So those data are out there. They tell you where the existing landslides are. That gives you a sense of where the potential future landslides might be, but be aware that Western Oregon is dominated by steep lands that's with sufficient loose sediments on top of seaward dipping rocks. And what invariably happens is because of our rainfall, high rainfalls in wintertime and things like that, that is all conducive to producing high landslide activity. So we have, we live in a high landslide risk environment.
Okay, so when we evacuate and run up the hill, then that might be a poor choice.
It could be a problem in some locations. Yeah, it could be a problem. I would like to think that if it's not sludge and with high sort of mud water content, it might be still navigable, meaning you might be able to still scramble over it. And again, like I said before, every step you can take towards high ground improves your chance of surviving, this type of event. Again, also, I think, the other thing to take home is that our evacuation maps are very conservative. They assume, in our numerical modeling, we assume zero friction. Buildings, trees, that's going to impact how the tsunami travels across the terrain. It's more than likely going to slow it down, which has an impact on how high it can actually run up. So we use zero friction because we're just automatically going to try and build a more conservative map product. So it basically assumes this whole landscape here is a concrete surface and the wave can run as far as it can until it runs out of energy. So again, what I can tell you is that the maps are conservative, and as long as you're moving in the direction of high ground, the chances are pretty good that you'll get to high ground fairly easily. Yes, the landslides could be a problem in some areas, and it's just something to be aware of and build redundancy into your sort of plans for where you might go.
Related to that, who determines the collection points for evacuation zones?
Yeah, great question. Invariably, that's actually done by the community. And so when we first started developing the maps in 2010 through 2013, the team at the time worked with every community on the Oregon coast and had meetings like this where they discussed, they showed the results of what the mapping was producing, and then they said, well, okay, where do you want to put your assembly points? And so that was actually a decision that was made by the locals at the time. Now we can actually implement changes if a community decides that one location is not the right one relative to another location. And we can certainly make those changes easily in a map-based product like what we have on the Nano site. And then it'll take us a little more time to actually roll those out into publication type maps, PDF type maps. So it can be done.
The collection point on South 3rd Street, basically, steers you right into an area of prior landslides.
Yep.
Has that been considered?
Not by us, no. So you're talking about an existing assembly area site that's been identified?
Yeah.
So all I can tell you is that at the time, the community made the decision to go to that particular location. And for whatever reason, they decided to, I wouldn't say ignore the landslide, but maybe, weigh up the relative risk between trying to get people to high ground and that slide actually being reactivated, and assumed that, that was probably the best sort of compromise is to still send people there. But I would argue that be aware of other possible routes that you could take. The other thing to consider is that in all our mapping that we produce online, we are not directing you necessarily to an assembly area location. We are trying to direct you to the nearest point of high ground to your location. And not every, which invariably means we're also forcing everyone to go on trails and roads. And in some cases, and actually in a lot of cases, a lot of those exit points are in areas that may not be able to accommodate hundreds or potentially even thousands of people. And so this is something that communities need to be starting to think about. And so, for example, in the case of Seaside, the conversation there is in terms of building vertical evacuation structures within the inundation zone at a level high enough to withstand a pretty extreme scenario type event. But that's another consideration that people need to be thinking about, and I know that emergency managers up and down the coast are grappling with this. It's a tough one, but it's something that you all should be aware of. So I think you had a question.
Yeah, you might have answered that, but a question about, when you look on the map at the yellow line, the yellow area, so those levels, what are they based on? And the prediction of how far the water is going to come in.
Correct.
You said it's pretty conservative, is that most likely will be less than that, but is that based on that average event that we were more likely to see? Was that based on like the worst case?
No. It was based on the worst case of the 5 t-shirt sizes. It uses the XXL inundation scenario, and the reason is simple. It's about life safety. And again, the decision to use XXL was actually not one that we drove. It was when the mapping was being done, we had a tsunami advisory council, which was made up of local stakeholders, emergency managers, commissioners, planners, etc. And they made the decision ultimately to go with the most conservative of the inundation scenarios. If you go to Washington State, they use our L1, which is akin to about a 3,000-year return period event. Our worst case is about a 5,000-year event. So they're using something that's not as conservative as what we are, and in part because they had bigger challenges on the southwest Washington coastline because there's just high ground is so far away from them. Ma'am?
What I never hear, this is great, thank you. I don't hear discussion about what happens to all the large trees that we have here and back to the landslide. So in between the landslides, I would imagine 3 minutes of violent shaking, our trees are going down. What's the example in New Zealand?
Yeah, that's a great question. To be honest, I'm not sure I have the answer for that one. I don't know. I haven't heard anything about. New Zealand landscape's a little bit different. The northwest part of the South Island's a little different to the Oregon coast in terms of vegetation. So I'm struggling with that one. I would speculate that obviously trees on sloping terrain, especially in wintertime, are likely to fail. And that's going to be another challenge in terms of navigating those. It's not going to happen everywhere, but it's certainly going to be a case. It's going to be out there. It's certainly something that you would encounter. Again, our environment is challenging because of the geology, the terrain that we have, the amount of rainfall we experience, especially in wintertime. In summertime, obviously, I would say it's a different kettle of fish and not as bad. In wintertime, it could be really bad.
Because of the saturation you're
Yeah.
talking?
Yeah. Luckily, the last couple of weeks have been beautiful on the coast and things have dried out a little bit, but, we were on target there for quite a wet winter, and we probably still are, to be honest, going forward. And it's that sort of super saturation of the ground on sort of a thin veneer of superficial sediment on top of rock. And when that water percolates down through that soil layer, hits the rock, it then starts sliding on that rock there. It just lubricates it. And that's why we would, we experience the landslides we would see what we experience now. And I would expect to see a lot more landsliding in a big event. Yep. Any other questions?
You talked about the shaking that will happen with an earthquake in distant areas, and that there would be plenty of time to have some warning. How do you define what's a distant earthquake as opposed to a close earthquake?
Yeah, okay, great. So for a distant event, you're not going to feel the earthquake. So again, we're talking about an event that happens up in Alaska, the Aleutian Islands, or Japan, or down in Tonga. Those are far field events, and so you're not going to feel the earthquake shaking, but you're going to hear about it. And you're going to hear about it because the National Weather Service, through NOAA, has a tsunami warning center in Honolulu. They also have one up in Palmer, Alaska. And both of those are basically monitoring seismic activity around the world 24/7. And so an event happens, it takes them about 5 minutes to figure out whether it's potentially tsunamigenic or not. It takes them another 15 minutes to actually make a decision, run their initial models, make a decision whether it's potentially that we need to actually get a warning or a watch or an advisory out to the public. So about 20 minutes after the event, you can expect to get a message from CNN or directly to your phone if you subscribe to NANUS or the Weather Service, etc. And then it's going to be, in the case of an Alaskan event, it's going to take the wave about 4 hours to get to our coastline. In the Japan event, it took 9.5 hours for the tsunami to reach us. In the Tongan event, I think it was around 10 to 11 hours. So, certainly in those far field areas, you have time, and you will hear about it. Now, you asked another question about how do you differentiate between distance and say a local event. So we sort of use a sort of qualitative difference of around 3 hours time to separate a distant event. So, for example, it is conceivable we could experience a smaller earthquake on the southern part of the Cascadia subduction zone, so down in southern Oregon, northern California, where only part of the slab in the face ruptures and slips. And that could produce a local tsunami down in that part of the coast. So Gold Beach, might get impacted by the tsunami. And it would be probably a smaller event compared to a full margin event. That event is going to take about 2 hours for it to get up the coast here. It's going to be like a distant event for Rockaway Beach. You might feel some shaking in that type of scenario. And it would probably, the general rule that we use is that if it's anything over about 40 seconds, it's probably Cascadia. If it's under 40 seconds, it's much more likely to be some sort of crustal fault that's moving. So, you hear about these magnitude 3s and 4s and 5s that are happening out at the junction between the Juan de Fuca Plate, the Gorda Plate, along that spreading ridge there. They're happening all the time. And, media will jump on it very quickly, or, earthquakes happened out there, and people start panicking a little bit. Those are not tsunamigenic type events. It's when we start to experience something happening within the slab interface, in the subduction zone, closer to the coast, that's when we might start to get a little bit more concerned. And again, in those types of events, if it's more than 40 seconds, it's probably Cascadia. A lot of those crustal faults are only a few tens of seconds, typically 10 to 20 seconds at the most. So I think I answered. Yep.
Yes, thank you.
Things will be quite different. I suspect that the jetty may not be functioning correctly after the event. I think that what could happen is that just through the earthquake shaking, I think there could be a lot of settling and potentially, failure of parts of the jetty. The tsunami wave could actually accentuate some of that as well. I think you could expect to see some scouring activity around the roots of the jetties, so on either side that could actually blow through holes and gaps. Not so much maybe in Tillamook Bay, but in other, like Nahalem Bay, that's very feasible. In terms of maritime traffic, no. You're not going to be moving anything through there for some time. I mean, those navigation channels will have to be, resurveyed, redredged. Small boats, I mean, the bar off the Tillamook Bay there will move probably. So you're going to need to get someone out there to try and map it and identify it. I know that both Lincoln, Tillamook, and Clatsop County had done some work with the Navy down in California to, as a means for post-disaster post-disaster activities. And so the thinking was, well, you could bring the fleet up from California and park it off the Oregon coast, and then send their sort of amphibious landing vessels onto the beach, bringing supplies, taking injured people off, things like that. So that's it's feasible. It's a concept that is not unreasonable. The problem is that in reality, the window frame that you can operate those vessels across this surf zone, it's pretty small. Our wave environment's just too big for a lot of those types of ship hops.
And all that's
So
gonna
it's
take
possible.
a lot of time too.
I'm sorry?
All that's going to take a lot of time.
Yeah, I mean, it's going to take them, I think, 3 days just to get up from San Diego
Yeah.
up to this coastline.
Yeah.
So,
Yeah.
again, it's days.
Yeah. I think we have one more question. Don, did you have a question?
No, I was just going to make a comment about the fact that the other waves coming in at 3 minutes or 33 minutes. So, and then you took care of it.
Okay. Any more questions?
Well,
Oh,
I said you were you and Chief Hesse were very accessible, but I didn't say how to contact you. Would you tell people in the community, like if they want to follow up with this and talk to you more?
so I'm in the office Monday through Thursday. You can come in and see me anytime, or you can email me at grace@corb.us, or you can call the city and use the directory to get to me, or Chief Hesse.
It's reassuring to see that your agency is looking at new technology and, making use of it the best you can. Is there any new technology in the works on predicting tsunami?
So, not so much in predicting. Predicting earthquakes is we're just not there. And I say that with a lot of caveats. So some of you may have heard recently in Japan, they had I can't remember the size of the earthquake, but it was probably mid-6 or 7 earthquake in an area that is expected to produce a megathrust, a great megathrust earthquake and a big tsunami. And they issued, for the first time ever, a warning to the community along that coastline to say that, basically there's a heightened risk of a possibility of a big event happening in this window of time. So that's the only example that I'm aware of something like that being implemented in the world. There's been discussions about trying to set up something like this in the Pacific Northwest, and time will tell. It's a challenging area. There are certainly, the scientific evidence seems to point towards there are certain periods of time when the subduction zone is going through what's called a slow slip event, where that strain is there, but in certain parts at the plate interface, there is roughly every couple of years there is some degree of movement that goes on, and there's been some debate about whether in those slow slip events there's a heightened chance of a cascading event fully erupting and rupturing at that process. So it's a challenging field. We're not there yet. We've got a long way to go, but we'll see what happens in time. In the world of forecasting and detection, there's a lot of research going on in that particular area. And like I said before, one of the challenges right now for the forecasting officers is determining whether an event is tsunami-genic or not, and how long it takes them to get a warning out. And the goal is that in time they want to really try and reduce that 20 minutes down to 5 minutes from detection to warning getting out there, because that's obviously critical for saving lives. And so there's technologies out there that researchers are looking into. Fiber optic cables is one area. Attaching sensors to fiber optic cables is something that people are actively researching now. Using high frequency radar is another technology that's being developed and applied up in Vancouver Island, using satellite-based technologies as well. So I think, in the world of forecasting, in the world of detection and issuing warnings, I think that's an area that looks very promising for the future.
Thank you.
Sure.
I've got kind of a two-part question. The first part is, obviously, there's a whole lot of input as to what is considered higher ground. Who determines how tall or how high up higher ground is?
Yeah, so it's all driven by the numerical models that we run. So we use basically one of the best tsunami models out there. We work with a guy who's been doing tsunami modeling for almost 2 decades. And all our tsunami models, not just for the state of Oregon, but for all the national tsunami states and territories, all our models are benchmarked so that they actually have to meet minimum requirements in terms of resolving physics, testing against known case study sites that have happened over the last couple of decades. So they're all tested against that. And then you basically force the model by some rupturing mechanism, which then creates that uplift. And then the model takes over and runs that wave in onto land. And depending on how much slip occurs out in the subduction zone, determines how big the wave is going to be, and obviously the extent of inundation that's likely to occur. So, and then of course the wave, as it's traveling across the shelf, is now interacting with features out on the shelf there. So I showed early on, well actually I didn't show, but there's, you can see variations along the coast in terms of wave amplitudes, interacting with Stonewall Bank, for example, off the Newport area, or Rogue Canyon down on the south coast, where the tsunami is actually channelized into this channel and creates much higher run-up elevations at those locations. So, the numerical modeling needs that underlying bathymetry and land elevation data to then predict where the tsunami is going to go. So we take that information once we've run the models. It'll give us flow depths and various other parameters, gives us run-up elevations. We then go one node more conservative beyond that run-up limit. And we did this for all 5 of our scenarios. And then, we ended up the community settled on using the most conservative of those to develop the evacuation map. So we think there's a lot of conservatism in there. The models that run these simulations are very good. They're well tested. We can always do better for sure. And I think, one of the science is evolving rapidly in Cascadia. The University of Oregon just received a $15 million grant 2 years ago to research the Cascadia subduction zone. And that work is going to be ongoing over the next 5 years. There's a lot of work being directed at better understanding the paleoseismology, the geologic history that's in all these estuaries and lakes, to refine those data. There's a lot of work going on in understanding the mechanics of earthquake ruptures. I mean, this is all stuff outside my area of expertise. So the science is evolving rapidly, and that's one of the cool things about it. We're just fortunate that we have one of the best records in the world in terms of our knowledge of these great earthquakes.
So all we can really do is be prepared, right? And that's why we're here. We really have no control over any of those. I would like to say that this would be a good time to talk about, if you'd like to be a part of preparedness in the city of Rockaway, please come talk to me. We have CERT, we have preparedness, we have RadioNet. All these things are ways for us to be prepared. I just want to thank John for being here. One of our What's yours? Are you a large?
Medium.
Medium. I got a medium. But thank you for coming up here and doing this for us tonight.
You don't have to do this, Jeff. Thank you.
That's it. Yeah, there you go.
Right on. Thanks very much.
Thank you.
Thank you.